Dangal greetings, I am James YUAN DALMACIO, the team leader of this group. And for our midterm online lab quiz 2, uh, we will present in this video our work entitled the Disaster Response Management System. So this project focuses on developing a system to help disaster response organizations manage and optimize the distribution of relief supplies during emergency operations. So our system handles different components involved in disaster response, including individuals such as responders and coordinators. We have also the affected communities, supply items, and delivery missions. It is designed to organize data efficiently and support decision making during critical situations. Overall, this system aims to improve how resources are allocated by considering important factors such as urgency, risk level, and operational efficiency. So, as a group, we have also my member, John Paul Consorte, to discuss and present to you the UML of this system.
Hello everyone, my name is John Paul de CONSORTE from 2CSA, and now I'm going to explain the UML class diagram for the program. So first, as you can see, each back represents a class which is a template for creating objects. Then the mission, which is the central controller, it orchestrates the entire operation by linking people, places, and supplies. The person, abstract base, a general category for humans in the system. It holds common data like name and sex. Responders and coordinator, specialized roles that inherit from person. Then community represents the target location, storing data like population and risk level. Then supply batch and supply item handle the logistic of the relief goods. So as for the understanding of the relations, the lines between the boxes shows these classes are connected. The inheritance, which is solid line with an empty arrow, responders and coordinator, two person. So this shows an is a relationship. A responder is a person. So they inherit the name and sex attributes but add their own specific data like assigned zone. Then aggregation, solid line with an empty diamond. Supply batch to supply item. So this is a part of relationship. A supply batch contains multiple supplies items. So if you delete the batch, the items still technically exist in the system database, but they are grouped here for the mission. The mission to supply batch. The mission has a batch of supplies assigned to it. So the association, which is the simple solid lines, mission to community and mission to responder. So this shows connection between independent objects. So the mission keeps track of each community. It is helping and each responders are working on it. Then the multiplicity, which is we have the 1 to 0 to many. One mission can have many responders. Then 1 to 1, which is one mission is usually assigned to exactly one community. And 1 to many. So one supply batch must contain at least one or more supply items. Then, so our UML diagram demonstrates a highly modular architecture. By using inheritance, we avoid redundant code for our personnel through aggregation. We can flexibly group supplies into batches. Most importantly, the mission class acts as a central hub using private data and public methods to calculate real-time efficiency and cost during a disasters. So now let's proceed to the actual code, which is the mission class. So the class starts with several private fields. So this represents the state of a mission. The object reference, instead of storing simple string, the class holds reference to other objects. List, responder, community, and supply batch. So this is a design pattern called aggregation. The mission has these components. Then primitive data uses double for precision heavy data like distance, difficulty, and mission cost. So, the constructor public mission, double distance, double difficulty. It sets the foundation of the mission. It initializes the array list for responders to prevent null pointer exceptions. It calculates the baseline metrics. So, for example, it defines expected time by assuming a baseline speed of 50 km per hour. This creates a standard against which real-world performance is later measured. Behavioral methods, which is the setters and getter. The class uses encapsulation. You can not modify the mission cost directly. Instead, you use assignment methods, assign responders, and set target community, which allows the mission to be built step by step. Then the accessors is the getters. This provides a read-only access to the internal state for reporting purposes. Then the computational logic. So the brain of the code lies in its calculation methods. So this processes the raw data into actionable insights. The compute mission cost method calculates the financial footprints. So it pulls data from supply batch, which is the value and weight, combines it with mission environment factor, which is the distance and difficulty. Then it includes a safety check. So if supply batch is equals to null, so to ensure the code doesn't crash if supplies haven't been assigned yet. Then the compute efficiency, which is method, which is the most complex structure elements. It uses a weighted evaluation model, which is supply score, time square, and time team score. So this structure allows the organization to prioritize certain outcomes like meeting community needs over like speeds. So output representation to string. Finally, the override to string method serve as the user interface layer of the class. So it uses a string builder to efficiently gather data from the community, responders list, and supply batch. It formats the raw doubles into readable string using string formats, which transforming technical data into emission summary reports. So now let's proceed to the another class.
Thank you, JP, for that wonderful explanation. So, my name is CAISTLER Joseph Escueta, and I will be the one explaining the person class. So, before we look at how the system runs, let's look at the blueprint for our human entities, which is the person class. So, the concept is in our system, we use inheritance to maintain clean code. The person class serves as the parent or superclass. It holds the common attributes that every individual in a disaster scenario has: a name and a sex. And the code highlights we use the protected access modifier for these variables. This is a strategic choice. It keeps the data safe from the outside world while allowing our child classes like responder and coordinator to access them directly without needing extra methods. So Rex will explain the methods, I, I mean the classes, which is the responder, coordinator, and the community.
Hi, I'm Gracia, and this is our disaster response management system. This is the responder class. The responder class extends person, extends the person class, and represents a worker who goes on mission. On top of name and sex, a responder has an ID, an assigned zone, and a performance rating. Mission completed, total success rating, total efficiency score. The most important method here is the Update performance. Every time a responder finishes a mission, you pass a success rating and an efficiency score. The formula is performance equals mission times 0.4 plus average success times 0.4 plus average efficiency times 0.2. This weighs mission count, success, and efficiency, reflecting that a youth responder isn't just active, they're effective in they're effective. This rating is later used in the mission efficiency calculation, closing the loop between field performance and system metrics. Next is the coordinator class. The coordinator also extends the person class and shares the same structure, ID, assigned zone, and a performance rating. However, unlike responder, it doesn't track mission or compute its own performance dynamically. The rating is simply set externally via set performance rating. Think of coordinator as an administrative role, managing zones and resources, while the responder is the operational role doing the groundwork. Both override Jet's role to, to return their specific label, which fits into the toString method output. Then, next is the community class. The community class models the people being helped. It holds the location, name method, population, list level, and urgency index. A computed priority score. The, the formula for priority is priority equal population divided by 1000 times list level times urgency index. This score determines how urgently a community list is. Larger population, higher risk, and higher urgency all push the score up. Crucially, the update urgency method lets you change urgency mid-program and automatically recomputes the priority score. So, the system stays responsive to changing conditions on the ground. To wrap up, these three classes form the human and social layer of the system. A mission links them together. It assigns responder objects to serve a community, uses the priority score to measure supply adequacy, and feeds results back into its responder, update performance. This design is lean, each class owns its own data and behavior, and they elaborate through well-defined methods. That's use object-oriented design. That's all. Thank you.
Thank you, Rex. Now I will be discussing the one of the important classes in our system, the supply item class and supply batch class. First, let's start with the supply item class. This class represents the individual relief goods that are distributed during disaster operations. This includes items such as food, water, and medical supplies. Each supply item contains several important attributes. We have the item ID, which is generally the generated using a static counter to ensure that each item is unique. We also have the category, which identifies the type of item such as food, water, or even medicine. Next is the base value, which represent the cost or value of the item. We also have the weight, which is important for calculating transportation costs during missions. And lastly, we have the priority level, which determines how important the item is during distribution. So, the priority level is automatically assigned using the method called determine priority. In this method, we use a switch case to categorize items. For example, medicine and medical kits are given the highest priority, which is level 1. Food items are assigned priority level 2, while water is level 3. And, and, and any other items are given a default priority level of 4. So this system helps, or this class helps the system decide which item should be prioritized during emergencies. We also included getters methods to access each attribute safely following the principle of encapsulation in OOP. And lastly, we override the toString method to provide a readable format when displaying the item's details such as ID, category, value, weight, and priority level. Now, let's move on to the supply batch class. The supply batch class is used to group multiple supply items together. This is important because in real-life disaster operations, supplies are delivered in batches rather than individuality, right? So in this class, we use two array lists. The first one stores the list of supply item objects, and the second one stores the corresponding quantities of each item. This method, add item, allow us to add a supply item along with its quantity into the batch. This make it flexible to handle different numbers and types of supplies. We also have a getter method to retrieve the list of items and their quantities. One of the key features of this class is its ability to compute totals. The method getTotalValue calculates the total value of items in the batch. It does this by looping through each item and multiplying it by its base value by its quantity, then summing everything. And similarly, the method getTotalWeight calculates the total weight of the batch, which is important for transportation and logistics. And lastly, we override toString method to display the contents of the batch in a clear and organized format. It shows each item along with its quantity as well as the value and total weight of the batch. So, to summarize, the supply item class represents individual relief goods with their priority and properties, while the supply batch class groups these items together and calculates their total value and weight. These two classes are essential because they allow our system to efficiently manage and organize supplies during disaster response operations.
Hello. So, thank you, Dalmacio, for explaining the supply batch class. So, now let's move on to the main class, where we put all these components to the test through 12 specific test cases. So, the purpose is act as our driver class. Its job is to simulate a real-world disaster response life cycle from the moment a community is identified to the final ranking of mission efficiency. So the workflow breakdown is the code structured into three main phases. So number one is initialization, which is test case 1 to test case 2. In these cases, we instantiate our objects. You saw earlier how we created zone A and stuck it with food and water. So next one is the operational logic, which is test cases 3 to 10. This is the meat of the program. Here, the main class calls complex methods from the mission class to calculate costs and efficiency. This one from test 3 to test 10. So, which is the next one is the reporting, which is the test cases 11 to 12. Finally, we use Java's array list and collections that sort to rank our data. This provides a clear summary of which communities need the most help and which responders are performing best. So, this is the output. So, if we look at the console output generated by this code, we can see the system's intelligence, which is this one. So notice how the mission cost in TC4 and TC10. When we added medicine to the batch, with the weight and value increased, and the system automatically recomputed the transportation costs. This proves our objects are correctly communicating with one another. So the data integrity. Look at the final summary at the end. It isn't just a list, it's a ranked report. By using the comparator logic inside our main class, we've transformed raw data into actionable information, successfully identifying that Zone A has a priority score of 88,000. 88.000. So to wrap up our presentation effectively, we walked through the technical architecture and the execution of our test cases. I'd like to conclude our presentation. So the core value, so what we have built here is more than just a collection of Java classes. By using object-oriented programming, which is OOP, we've created a scalable framework for disaster management. We've automated the most critical part of a crisis, which is decision making. Through this project, we demonstrated precision, how formulas for mission cost and efficiency ensures resources are never wasted. Responsiveness, how the system adapts in real time when community urgency or supply levels change. Next one is accountability, how our responder performance tracks ensures that the best equipped individuals are leading the most difficult missions. So in a disaster, every second counts. Our goal with this system was to ensure that while the situation on the ground may be chaotic, the management of the response remains organized, efficient, and data-driven. So thank you for your time, and we are now open for any questions regarding our code and logic. Thank you so much, sir. That's all.